In this session, we shall discuss about the shortest job for scheduling. So in this algorithm, it will be associating with each process the length of its next CPU burst. So when the CPU becomes available, it is assigned to the process that has the smallest next CPU burst. So it comes with the two schemes. It is non-preemptive and then preemptive SJF. Non-preemptive is once a CPU is given to the process, it cannot be preempted until it completes, or else it will be requesting the input output. But in case of the preemptive, if a new process arrives with the CPU burst length less than the remaining time of the current executing process, then that particular process will get preempted. So otherwise it is called as shortest remaining time first algorithm. So we shall discuss with the simple example of non-preemptive SJF. So all these four processes are arriving at the same time, and these are all the corresponding burst time. So here we'll be discussing about the non-preemptive shortest job first algorithm. So based on this, we have drawn the Gantt chart. So among the four processes, the P3 will be having the lowest CPU burst time. So that will be allocated first, and for 1 millisecond it will get executed by the CPU. And next chance is given to the process P2, and it will be executing for another 4 millisecond. And P4 will be given a third chance. And after that, the final process will be executing is P1. It will be occupying for another 6 milliseconds. So totally burst time is 16 milliseconds. So based on this Gantt chart, so we have calculated the average waiting time and then the turnaround time. So it will be producing as 4 millisecond and 8 millisecond correspondingly. And next is about priority scheduling. So it is a special case of SJF algorithm. And here, instead of this priority, we will be assigning a priority number with each and every process. So the priority may be the smallest integer will be treated as the highest priority number. Again, the priority scheduling will also be a preemptive and non-preemptive in nature. So non-preemptive approach will simply put the new process at the head of the ready queue, which will be having the highest priority. But in case of the preemptive approach, the CPU will be preempted if the priority of the newly arrived process is higher than the priority of currently running process. So it is termed to be a preemptive priority scheduling. The main problem with the priority scheduling is starvation. So that is, low priority process may never execute. So to provide a solution, so gradually you are going to increase the priority periodically. So at some point of time, the low priority process will get the high priority number. So automatically that low priority process will get executed by the CPU. So the solution is termed to be an aging. The last algorithm is round robin scheduling algorithm. So again, it is a special case of first come first serve. So in the earlier discussion we have given this FCFS as a non-preemptive scheduling. So with FCFS we are going to add the preemptive nature. So that comes under the round robin scheduling algorithm. So here each process will get a small unit of CPU in a fairly manner. So this small unit of CPU time is said to be a time quantum. After this time has elapsed, the process is preempted from the CPU and added to the end of the ready queue. The second turn or third turn, so the corresponding process will get chance to execute the process in the CPU. So the no process will wait more than n-1 into queue time units. The round robin algorithm's performance is based on the time quantum what we set. So if the time quantum is large, then it will be treated as a traditional FCFS algorithm. If the time quantum is very small, then Q must be greater than the context switch time. Otherwise the context switch will happen frequently. The context switch is an overhead, and if it is too high, it is not going to do any useful work. So we can explain this round robin algorithm with an example. So here we consider the time quantum as 20 millisecond. So there are 4 processes available, and these are the corresponding burst time. So we have allocated the P1, P2, P3 in a FCFS, but only for time quantum equal to 20 millisecond. So initially the P1 will be entering, and only for 20 millisecond the process P1 will get executed. So after the time expired, so we'll be giving a chance to the next process. So the remaining 33 millisecond will get executed in the next turns. So likewise P3, P4 will get executed only for 20 millisecond in the first round, and in the second round the process P1, P3, because the P2 in the first round itself it gets completed. So this is how it will be proceeded, and finally end with the final millisecond as 153. So with that we can able to calculate the average waiting time. So here this is a special case how to calculate the waiting time. So for the process P1, so we have to consider the final turn of the process P1 when it get executed. So P1's waiting time is 112. So earlier it has executed for 2 times. So 2 into 20 it is about 40. So if you are going to subtract 140 from 112, we'll be getting 72. So for the process P2, so it is only one time it is executed, so the waiting time is 20 millisecond. If we consider the process P3, so the final turn it is about 145. So we have to consider the earlier execution time. So here it is executed for 1, 2 and then 3 times. So 3 into 20, 60. So from 145 we have to reduce 60 and we'll be getting 85. So likewise the process P4's waiting time will get calculated. So the turnaround time or completion time also will be calculated as waiting time plus burst time. So we'll be getting it. So for example, for process P1, waiting time is 72 and the burst time is 53. So put together the turnaround time will be of 125. So based on this we can able to calculate the average waiting time and then average turnaround time or completion time. So based on the time quantum, it is going to have a more impact on the performance of the round robin scheduling algorithm. If the time quantum is 12 and we'll be having no context switch for executing this particular process. If it is 6, so one time we are going to do the context switch. If the time quantum is very low, so frequently are going to have the context switches. So we have to have a priority in setting the time quantum, so which will be enhancing the performance of the round robin scheduling algorithm. So this is a reference taken from the syllabus cache Galvin operating system concepts. Thank you.